Right, hello everybody, and welcome to our last topic for this course. Let me just check if my sound is doing what I think it does. Okay, so that looks get something to write on. Are ready to go. Now I allowed 3 days for this last topic. We'll see how far we get. I don't think we necessarily need that much time, but it just means that we are not in a hurry, which is good. All right. Just to double check. Can everyone see? And oh, cannot see me. Let me double check. I shared the right screen. Audio is good. That's good. Still can't see me? Can I write stuff on the screen? Scribbles. It's good on YouTube. Okay. That's good to know. That is weird. I'm sharing screen number 2. Let me check. Stop sharing. Let's see if that screen 2 is definitely that one. Really can't see it. Oh, that was weird. That's exactly what I did. Technology. Always keeping us on our toes. Otherwise, it would be boring. All right. Good. Thank you for letting me know. Okay, now we're ready. So, What we are doing in our last topic is revisiting, in a way, or expanding the topic of area and adding some volume concepts on top of that. So we're going to start really with a length concept, then an area, and then a volume. So the length concept is going to be the perimeter. When I have a shape, maybe a nice polygon, maybe a not so nice polygon, the perimeter is simply the sum of all the side lengths all the way around. In the case of a circle, we call it the circumference. I guess you could call it the circumference, but people tend to use the word perimeter for a shape that has line segments. Now, this isn't a complicated concept, but it does require that I need to know the side lengths in one way or another. And it is an elementary school topic, so fairly relevant. Let's zoom in on this first one and just do it by example. Regardless of the shape, there isn't really a shortcut for us. We need to figure out the lengths of all the sides and then simply add them up. So let me just copy this triangle over as we're doing exercise 17.1. Let me see, where is my... That right angle triangle, sort of. Sort of. And we have a 30-degree angle here, a 1 theta if I need it, which I doubt I will, and a B and a C, just for me to keep track of things. So I don't really care about the angles, though theta is easily calculated as 60 degrees. I might not need it. I try and use as much of the given stuff, the given information, as I can, and just build on that. So we can go and say, maybe find B. There isn't a specific order here. I just maybe wanted to find B first. I can do that by saying, well, the tan of the angle that's given is going to be opposite over over adjacent. I'm not using C yet, so B over 1. And that then tells me that B is, well, I multiply both sides by this denominator, which just happens to be a 1, so it doesn't affect things. But in other cases, it might. And let's do that and remember how our specific calculator works. Yours might, whatever calculator you have that you will use in a test, make sure that you are comfortable with it. I have tan d for degrees in MathBot. MathBot has its own command for the function or function name. Because I'm using degrees, I need to tell it, and that's what that tan d does. So if we round it, we have point, let's use a few decimals, 5774, maybe. Just rounding to 2 decimals, if they don't specify, it makes me a little nervous. 4 makes me a little bit more comfortable. But regardless, know that I shouldn't use a rounded answer in a future calculation or a presentation thing. I don't want to write all the decimals all the time. But I have B. Whoopsie. Let's actually see if I can store B in the memory. Let me try. See if that worked. No, MathBot didn't like that. I'll have to figure out how that works. Maybe the capitals. It doesn't like the capitals. I'm going to try one more. Just to see, it would help if it can store it. Okay, that worked. Just test if I see the 0.577 B. No, capital. Huh? Okay, good. Now we have our B. And your calculator will, of course, have its own memory function, but it does help me if I can use a memory function of some kind to not have to type in all the decimals or anything, right? So I never have to worry. It's stored the most accurate version. And your calculator, the new scientific calculators definitely can store a couple of um, numbers in its memory. Okay, so that's good. So now I kind of have a choice in terms of, I need to find C. So I have, I guess, oh, stupid line. I guess I have two choices. One choice is I can use Pythagoras and the b that I have to say that 1 squared plus b squared equals c squared. Now I have the b, so whenever I need it, I'll use that number, but I don't want to put a rounded one in here. So c squared, let's just say c is then the square root of 1 squared plus b squared. So when I calculate that, let's see what we get. Calculator heavy, I suppose. 1 plus b squared. Get there. Get 1.1547. Still rounded, but I think that's pretty good. Or we can use trigonometry again, right? And ignore the b, because what if I made a mistake? Then if I use that for c, then c would be wrong. But if I try and only use things that were given, I am a little safer. So I can use cosine of the given angle 30 because that is the adjacent side over the hypotenuse side. And then c is equal to 1 over cosine 30. Cross multiply or flip everything or however you are comfortable doing it. So let's see if we get the same value for c, because of course we should, right? Let's actually store c so I don't double up on everything. 1 divided by cosine. Good. Oh, I didn't see c. Haha, c, c. Nope, that's the wrong c. Oh, it recognized that, so that's not case sensitive. Okay, that's good. Is it the same? Yeah, it has to be the same, right? We didn't round anything. So of course, it is exactly the same. So you do have options, and it's good to know those options. I would probably do number 2 because it doesn't rely on a previously calculated answer where I could have made a mistake. Or do both, and if they are the same, then you have more confidence. Either way, you can choose. So then the perimeter is 1 plus b plus c, and we just add up all our answers. Let's see what we get, and of course, we have to use the most accurate versions. Plus b plus c, and we get 2.721 if I round it. So do pay close attention to what the question is asking in terms of rounding. Should I round to 2 decimal places? Should I round my final answer to 4 decimal places? Do whatever it says you should do, because I've seen people just lose marks for no reason by not following specifically the instructions of the question. Because a part of the question might be to test if you know how to round decimal numbers. So please be aware of that. But the concept of perimeter, not a very complicated one, I hope. Okay, let's see what is next. Maybe a more interesting shape. Let's move it back. Let's go down. I have another triangle. Do we really have to do two triangles? Pretty straightforward. Let's at least talk about the second one. That's what you just find the perimeter. So uh, it's the same, right? It's exactly the same. And we've done everything in this we've done except adding the numbers, which is a pretty simple step afterwards. So I don't want to bore you with triangles again. Let's talk through this. How would I go about doing it? I'll use the 45-degree angle, even though this one's 45 as well. Let's suppose we use the top one. I would use the tan function again, because that uses a and 3. So tan of 45 would be 3 over a. And then I can solve for a, just like we did, pretty much. Then I can go Pythagoras to find c, or I can use the sine function, because it's opposite over hypotenuse, find c, and add them all up. If you're not sure, give it a shot. Show me how far you got, and let me know. Let me know. But I'm pretty sure, based on what we've done before and our trigonometry chapter, pretty sure we can handle that, and we should. So let's go to something maybe a touch more interesting. Now, I understand this one isn't showing in the book for some reason, but just uh, bear with me. I'll draw the shape for you in number 1, and number 2 we can see. So let's what's that number? 17.2. Exercise 17.2. It's gonna be a parallelogram. Just fill it in the book. I'm not sure why it doesn't show. It doesn't like the picture format or something. Who knows? Parallelogram. So that should probably be highlighted that this is parallel and that one is parallel to that one. We have a length here, which I think is a 4. We have this side length, which is a 5, and this side length, which is a 6. Just made up numbers, right? Find the perimeter. Now, I do this one because I've seen people in the past forget that we're doing elementary school stuff for the most part. And sometimes all the numbers are just given. There's no fancy things for me to do. I need to find the perimeter. Well, this top, because of it being a parallelogram, opposite sides are the same length. So that one's 6 and that one's 5. And the perimeter is just adding up all the numbers. Let's go around this way. 5 plus 6 plus 5 plus 6. And, oops, it's an ugly 6, I apologize. And by them giving me this, I guess, height of the parallelogram, doesn't play a role in the perimeter calculation. So I have 22. And I'm done. Sometimes a basic question like this is given just to see, do you know what perimeter is? And do you know to not overthink everything? That is also quite important, right? Don't overthink everything. Don't always expect the worst. Sometimes it is just that straightforward. Let's check the other one. So this was number 1 that did not show in the book. Maybe it was shy because it was so straightforward. Who knows? Let me just move this to the other side so I can copy next shape. Whoa. That was aggressive zooming. Okay, what do we have? We have, let's go like, copy the shape, a little top side here, more angled there, and then like that. Have some side lengths, 8, 10, and we have this down 7, so perpendicular down. Yeah, like it. We have this trapezoid that we want to find the perimeter of, which just means we need to calculate all the side lengths, and the only one missing is this bottom one. So let me break it down into sections. I can go from this top vertex down perpendicular as well. That would be 7. And let's break it up into, what do we let's call it A, B, and C. Doesn't matter, right? Just for us to keep track of it. Actually, I didn't need the B, right? The B is obviously 3. So actually, I only need 2 lengths to calculate. And I'm back to triangles, which is really the shape that I know the most of. So going back to triangles, you'll see a sort of a recurring theme one way or another. So let's find A. I can just use Pythagoras. Say A squared plus 7 squared equals 8 squared. So A is then the square root of 8 squared minus 7 squared. I take the 7 squared over first and then get the square root. What do we get? Now we can calculate the square root first, 64 minus 49, or we could just do it all in the calculator. Now I want to remember this A so I can use it in a future calculation. I have to do it maybe from the start. Your calculator can maybe do a memory function afterwards. Everyone's different, right? Let's call that A, and let's make it the square root of exactly what I have here. I can at least do 64 minus 49, maybe like that, right? Let's see it at least so we can write it down and double check that it is in the memory. 8730, I guess, rounded to 4 decimal places, if that's what the question wants. Double check the specific question. And if it doesn't say anything, then you can round it to whatever. It doesn't really matter because in a future calculation, you never use a rounded number anyway. So it's all really just presentation, right? No, not B. We've already done B. There is no B. B is a lie. C. C, I do exactly the same thing, but for this triangle. C squared plus 7 squared equals 10 squared. I can't trust that, oh, this A looks less than 3. It's just a random sketch, right? Can't trust it and actually measure this perfectly, even on a printed version. So C, after I take the 7 squared over and then take the square root, 10 squared minus 7 squared. Let's do that. I will calculate it as C and square root. I'll just type in 100 minus 49, like so. Let's see what C is. C, whoops, is 7.114. Right, so then the perimeter, reason we do it first because it's really the simplest one of them all, is simply let's go all the way around. Let's go 8 plus 3 plus 10 plus C plus 3 plus A. I don't have to write the decimal versions in there because they're over there and they're over there. I do want to count them all and calculate this. Let's do it. 8 plus 3 plus 10 plus C plus 3 plus A. And we get 35.0144 rounded to 4 decimal places, which was just my choice. I pretend the question said 4, so I practice my rounding where I can. So I think when it comes to perimeter, we don't need more examples. We are sort of stuck with needing all the different line segment lengths. I could maybe split it up according to simpler shapes that I have more knowledge of, like Pythagoras and so on, but I still need all the lengths all the way around in some way. All right, perimeter. Now for this last topic, I want to include the circle as well. Even though it's not a polygon, it's a shape that occurs often, and I want to know all its properties as well. Let me make a new page here. And when it comes to perimeter, we have already done that, right? We call it the circumference. And it was a part of our discussion to find the constant pi, actually. So I just want to circle as we do the little subtopics here. The circle is part of what we want to focus on. The perimeter of a circle is called the circumference. Special, so it has its own name. And the circumference of a circle, let's draw, let me not freehand the circle, that'll just be embarrassing. Let's do it like that. T. Let's say we have a radius r. Circumference is simply 2 pi r. Easy enough formula to remember. Remember because pi was the ratio of the circumference over the diameter, and the diameter is 2 times r. So if I solve for circumference, I get 2 times r times pi, or 2 pi r is how I remember it. Okay, so perimeter or circumference of a circle, we have already done, just worth remembering. So the perimeter topic is pretty much done, right? Not much more we can say. Check book. So we want to move on to area. Area. Now I realize we've done some of it. We've done the basic area formulas for do triangle. We did, of course, the square and the rectangle and the parallelogram and the trapezoid, those basic shapes. But we were sort of limited to formulas specific to that shape. We want to expand on that a little bit, and our goal is still very structured, very structured. So let's stick to a regular polygon, but let's not look at specific number of sides. Could be a triangle, could be a square, but we know those. What about a regular pentagon, regular hexagon, regular polygon with n sides? So we want to find a formula that I can tell the formula, this is the size of my regular polygon, and the formula will give me the area value. So the formula is the area. If I have a polygon, let's say here the side length is called S, S for side length. So maybe I have a little pentagon here, it's regular. Each side length is S, right? S all the way around. And I have 5 of them. So N counts the number of sides. S is the side length specifically. Then the formula is going to take S, square it, multiply it by N, divide by 4 times the tan of 180 degrees over N. This formula, admittedly, is a little bit less pleasant. Now, I've been debating back and forth, and I think it might be worth it to just get a taste of where a formula like that could come from. But I'll make it clear, do not panic. Do not panic. The only thing we have to be able to do in a test is use the formula, understand how to use the formula. But I'm never really comfortable with just using a formula if I don't know where it comes from. I might not be able to duplicate it. I might not be able to understand it perfectly, but I've seen it before. I have the flavor, I have the idea, and it just doesn't feel as made up as when the formula is just given and I just have to trust it. By seeing where this comes from, it makes math a little less mysterious. So let's just see, where does this formula come from? It's nice. I like it. Let's have a look. Let me just move my stuff. So my Pentagon here isn't a very good drawing. Let's make another one. Let's ignore that guy. Let's make a hexagon. Hexagon's going to be a little nicer. I have to draw a hexagon, right? Ooh. Fairly big. Supposed to be regular. It might not be perfectly regular. I think my bottom side's a little big, but it's not bad. Something went wrong over here on the right. Doesn't matter. It's just an idea, something to look at, right? Now, I'm not married to the hexagon, but it's a decent size to get the idea. So I'll have a center point, of course. So this is true for any polygon. I can split it up from the center into triangles that are all the same. Now I'm freehanding this. Triangles, because it's regular. I know mine's a little flat, but these triangles are all the same. All these triangles are the same. And the number of triangles, so I can split my n-gon into n triangles. All the same, and we call it congruent. They're exactly the same triangle. Same, which means they'll have the same area. Which means if I just focus on one of them, let's focus on this bottom one. To make it pink. If I focus on one of these triangles, and I can find the area of this triangle, well then, I'll just multiply this triangle in the hexagon case by 6, in general by n, and then I would have the area of the polygon as well. So let's make a plan. Oops, that was a little ugly. the area of my n-gon, it's regular, right? Remember, it has to be regular. As soon as I lose that, whew, then it's really handled on a case-by-case basis. The area of the n-gon, n-sided polygon, think of n here as 6 in my hexagon case, is equal to n times, I'm going to write it in pink, the area of this single triangle. Coming up with a plan. I split it up from the center into triangles. I have all the same triangle. So now I can focus on a single triangle. And I have the side lengths, right? That has to be given. Side length is S. I know my S looks like a 5. It's not, it's an S. Let's make it a little more curly then. That just looks weird, but okay. So now the only question is, can I figure out what is the area of this single triangle? So the rest doesn't matter now. Only this triangle matters. Okay. Now I understand the area of a triangle. Should we continue in pink? I don't know if it's going to be too much pink, so let's maybe not. So the area of the single triangle is, of course, a half times the base times the height. Throw the height in here. Height. But I have the base. The base is the side length S. Side length is given from the start. I need to know the number of sides of the regular polygon. I need to know the side length, which is, of course, all the way around the same. And the formula can then calculate it. Well, I'm trying to come up with the formula. Where does this guy come from? Where does this formula come from? It's unpleasant. It's made up? No. Okay, so I don't have to really worry about a B base. It is the side length S. That is the base of the triangle. So now I'm systematically figuring out, what do I really need to know to finish this area of my regular n-gon? Well, it's n times the area of a triangle. Okay, so what I really need to find is, what is the area of a triangle? Okay. Area of a triangle is a half times the side length S times height. So what I really need to find is the height H. Okay, so this is now what we need to find H. Well, that's not going to be a one-step process. If I go around this center point, all the way around, in one way or another, all the way around is 360 degrees, right? But I have one triangle, two triangles, three triangles, four triangles, five triangles, six triangles, all contributing to this 360-degree full rotation angle. This one contributes the same amount as this one, the same amount as that one, the same amount, as well as the pink one. So this angle here, let's call it, let's call it nothing right now. Top angle of my pink triangle. I'm trying to make this as clear as possible. Is 360 degrees split into, in the hexagon case, 6 equal pieces, but in general, n equal pieces. When I look at my pink triangle, I can say, well, I can't really use this angle completely. Let's just look at this little angle, theta. And when I take the perpendicular line down to the base of the triangle, it splits the top one into two. So theta, that was an ugly theta, theta is a half of the top angle, which is then 180 degrees over n. That's my theta. And I need this because I want to get down, just like before, really, in one way or another, I want to get down to a right angle triangle. Let's make it blue. So I want to get to a right angle triangle so I can bring in my trigonometric functions, because they're going to relate an angle to a side length. So if I look at this blue right angle triangle, well, I have a side length here, this bottom one, which is a part of S, which is exactly a half of S, because I split this in two. I have my theta, and I want to find H. So let's write it in blue, because it's coming from this blue triangle. We're almost done. So what do I have here? I have the opposite side and the adjacent side. So I then have tan theta is the opposite side over the adjacent side. This then tells me that H is S over 2 over tan theta. If I clean this up a little bit, H is S over 2 tan theta, which was 180 degrees over n. And you see slowly where this formula is starting to take shape. Not quite, but you see the tan popping out. All right, so we have H, which we need to find the area of the pink triangle, which we need to find the area of the polygon. I know, just a little step forward and things get a little messy. So in H, now let's just keep track. Now we have to sort of reverse engineer this, right? What did we do originally here? We wanted to find the area of the polygon. We needed the area of the pink triangle. Or the area of the pink triangle is a half times S times H, which I now have found over here. So if I insert that, and I'll pretty much stop there. If I insert this H in here, I'll write it nearby. S over 2 tan 180 over n. You see I have a half, so I divide by another 2, so that's going to become a 4. I multiply by another s, and there's an s there already, so I have an s squared. And then when I put that answer in here to get the area of the polygon, I multiply by n because there are n of these triangles. So I have an n at the top. And we'll get our formula. So like I said, don't panic. Some people, like myself, like the fact that even though I don't remember everything perfectly, I have seen where things come from. I have seen why formulas are the way they are, and I can sleep at night knowing it's not magic, it's not made up. There's a logical, stepwise procedure to get to these formulas. But just using them is a different story that I won't think about where they come from every time just to use them. So it depends on my goals, right? Now that I have seen it, I feel a little bit better about the formula personally, but it doesn't affect how I just need to practice to use it. So in our last little bit, let's see if there are questions that ask me to use this. Book again here. So there's some in 17.3. Now, because these are all regular, they don't have to draw the picture for me. They can just tell me, draw a square with a side length 3 and use the formula to find the area. Practice it on an equilateral triangle with side length 2, a regular pentagon with side length 1. Right? I can do this. I can use this formula for any regular polygon. So they ask me for a few, and they ask me for some simple ones that I happen to have a formula for anyway. If I look at the square and I have a side length 3, then I know already the area is 3 squared, so 9 square units, whatever the units are, I don't care right now. So because it's a square, I can verify it with my specific formulas. But let's practice this area, this more comprehensive area formula. So I'm going to write it like this: s squared times n. I'm just going to copy it down. 4 times tan 180 degrees over n. So now n is 4, side length is 3. That's what they gave me. So I can put in those specific values. So I get 3 squared times 4 over 4. 4 times tan of 180 degrees over 3. No, not over 3. Not over 3. Over n, which is 4. Right? I have to put these things in the right places. So let's calculate that and see if we do get our 9, as we of course should. We know the area of a square. That's not the issue. So let's see what we get. So I have 3 squared times 4 divided by 4 and divided by tan in degrees of 180 divided by 4, like so. And big surprise, which should not be a surprise, I get 9. I should have gotten 9. So this is a way that we often do this. If we have a fancier situation, fancier formula, we apply it to something we already know the answer to verify that it works even in these simple cases. So that's good news. Now, of course, when you just have to calculate the area of a square, it doesn't matter which formula you use, right? If it doesn't specify. Random line. But even in the case of a triangle, if it just says I have an equilateral triangle with side lengths 2, they're all the same, then I might not want, I can find the height of the triangle, split it into 2, use Pythagoras, do your thing, you can do it. But this formula allows me to not care about that. It doesn't require that I know the height in my half times. Sorry, I'm writing and speaking different things. It's hard. In my half times base times height formula. It's a different formula to find the area of this triangle. But again, I do have options. In this case, n is 3 and s is 2. That's given. So let's plug them in. Side length 2 squared times number of sides of the triangle 3. 4 is always a 4. Tan of 180 degrees over 3. N is 3. Let's plug it in. Practice your calculator stuff. It's important. So 2 squared is 4 times 3 divided by 4 divided by tan in degrees 180 divided by 3, and we get 1.7321 if I round it to decimal places. Just an alternative. If I happen to have uh, a polygon that is simple enough, I already have a formula for it, then use whichever one you want. But depending on what's given, even to find the height to use my simpler formula, there's Pythagoras and all kinds of stuff. Do I want to do that? This is kind of simple once I get used to it. So know your options and pick the one that is the safest. But of course, as soon as I step away from, we're almost done. As soon as I step away from triangles and squares, then kind of don't have a choice. Let's draw a pentagon here. Freehand-it, why not? All the same. Side length is 1. I don't have a formula for this one. This is my formula. S squared times n over 4 tan 180 degrees over n. And in this case, n is 5. S is side length 1. So let's plug it in. 1 squared, 5 for n, 4 stays a 4, tan of 180 degrees over 5. Let's see what we get. And then we are done for this session. I don't need to write the 1, it's 1. 5 divided by 4, tan in degrees, 180 over 5, like so. And we got 1.7205. So get used to the formula if you're interested to understand where it comes from. I didn't want to leave it out. It makes me feel better having seen where this formula comes from. It demystifies it a little bit. That's the intention. But I won't ask you to derive the formula, just use the formula. Make sure you understand how to do that, how your calculator wants you to do that, because silly calculator mistakes are very unfortunate. So we'll pause here in the discussion on, I guess, perimeter, area, and eventually volume. A little bit more to do, but for now, let's focus on the basics. Brush up on perimeter if you need to. Place to start. And then understand this formula to find the area of a regular n-sided polygon. Are there any questions on this at this stage? All right, then we will continue this question. Yes.
Yeah, I was just gonna say, it's probably just a me issue, but I keep getting the wrong answer in my calculator for the last
No,
one.
it's unfortunately common. Uh, but I'll end the session here for the video's sake, and then we can talk about it. Stay afterwards, and we can talk about it if you need.
Okay, thank you.
Right. Just end the YouTube video.